welcome to our third talk of our CPAIOR Masterclass 2020. This talk is devoted to metaheuristics. So here the talk will be longer than the previous two. So this one will last about an hour and a half, and it's divided into two parts. So we have two speakers, Professor Andrea Schaerf and Professor Günther Raidl. In the first part, which will be roughly 40 minutes, Andrea will talk about simulated annealing and local search. And the second part will have Professor Günther Raidl talk about reinforcement learning and how can we learn meta-heuristic approaches and these kinds of algorithms. Now, how we will do the questions is we will first have one part, and then we'll ask questions, and then we'll have the second part, and then follow up with questions. So it's my pleasure to introduce the two speakers. So we have, as I already mentioned, Professor Andrea Schaerf. He's a professor at the University of Udine and has a long history in local search and local search and meta-heuristics for combinatorial optimization problems. Probably it's fair to say with a specialty in scheduling and timetabling algorithms. Apart from that, he's also developed various tools, like for example, famous, let's say, Easy Local, which is a C++ framework for local search algorithms, and has also developed other kinds of problem specification languages. In the second part, we'll have Professor Günther Raidl, who is here, as you can see on the camera. He's a professor here at the University of TU Wien in Austria. And his main research interests include algorithms, data structures, and in general, combinatorial optimization, perhaps with a focus on meta-heuristic approaches, mathematical programming, and the integration of these two. And of course, as we will see today, he will also talk about how can we learn these meta-heuristic approaches automatically. Okay, so that said, I think we can now start. So I'll now give the floor to Professor Andrea Schaerf.
Thank you, Emir. So can you hear me?
Yes, you can hear you clearly.
Okay, thank you. So this will be the first part. So we'll be mainly on local search and more specifically on simulated annealing, but also other techniques. That's why I named simulated annealing and friends. Okay, so this is the outline of the talk. So we'll talk about local search very briefly, because I assume that everybody knows at least something about local search, known also as a neighborhood search, but just to set up some terminology. Then we move to simulated annealing, and we will see which are the key components and variants of simulated annealing. Then we talk about parameter tuning, a little bit about applications, because we don't have time about it, and discussion and conclusions. Okay, so let's start with local search. So probably everybody has seen this picture in some form. So we start from an initial solution. So the initial state is selected in some way. So we will get to that back later. And then what we do, we explore the neighborhood in some form. Again, I'm very general about this because I'm not saying that we explore the full neighborhood. We do some sort of exploration and we select a move. So, and also in some way we select one of the neighbors. So, and so this is, we call states, these points in the search space, and we call moves with the M, movement, the description of the movement. So we select the move, then we ask if this move according to our method is acceptable. If it's not acceptable, we remain there. If it's acceptable, we move, we apply it. We also ask whether this is improving the best that you have seen so far, and we go on. Okay, so we go, then we ask whether our stop criterion is met. The stop criterion can be anything: computational time, number of iteration, stagnation detection, quality reached, and things like that. So anything can be a stop criterion, and then we go on. If the stop criterion is not met, we go on, and so forth. Okay, at some point we end up in the what we call the final state when the stop criterion is met. Obviously, we have no guarantee that this is the global optimal solution. This is, in most cases, a locally optimal solution. Okay, so now let's go to the meta-heuristic, which are the way to make all these decisions, which part of the neighborhood we select, how do we, whether we accept or not, when we stop, and so on. Here, actually mentioning also meta-heuristics which are not based on local search, so general meta-heuristics. Okay, so this is the history to show that the oldest one is simulated annealing, then the others came afterwards. At some point, we had an explosion of new meta-heuristics. So in the years 2000 and following, we have all kinds of animals and natural phenomena like bees, cuckoo, harmony search. There was a very large number of new meta-heuristics, either local search based or not. At some point, somebody said maybe this was too much. So there is this very nice paper by Kenneth Sorensen, which says that maybe we should stop inventing new meta-heuristic, but we should instead understand the components of the meta-heuristic. So many of these new ones actually are not new at all, but just a combination of components of the others already known. So we should understand which components are more important, how we combine them. Okay, so I totally agree with this paper. I encourage you to read this paper by Kenneth Sorensen. Okay, so let's now go back to the first one, so which is simulated annealing, which is our starting point. And so what's the very brief history of simulated annealing? So simulated annealing started by these two papers, which are known as independent, by Kirkpatrick and others, and by Czerny, that started the idea that we will discuss. Then after a short while, the idea was considered very good. So after a very short time, we already had some books on this, on simulated annealing. So that meant that the field was already mature enough to write some books on that. And then we had some other, let's say, systematic analysis of the behavior of simulated annealing, mainly done by David Johnson, that is a very well-known computer scientist. So very good reputation. So this is the prehistory, let's say, of simulated annealing. My favorite papers are, okay, just to mention that now we have 8,000 papers on Scopus with simulated in the title. If you go from the title to the abstract, the number explodes. So it's much larger than that. My favorite reference are these two. So the book by Van Loren and Arts, and the first of Johnson's papers. I think these are very beautiful references. So again, I encourage you to read them. Okay, so this is the pseudocode of simulated annealing. So I try to make it compact. So maybe I remove some details, but I hope this is understandable enough. So we have this notion. Okay, I'll go quite quickly. I have this. Obviously, we have some parameters. So we have the search space of the problem, the neighborhood relation, so how we define that two states are neighborhoods, the cost function that guides the selection, and some parameters that we will discuss now. So initially, the temperature is set to the start temperature that we call T0. We start from a random state. So we select a random point in the search space, and we initialize the best solution found so far. So while the temperature is still larger than the final temperature, so TF is the final temperature, what we do, we start a counter. So N is the counter of the number of iterations at the given temperature. So while N is smaller than the threshold of number of samples at each iteration, we select a random move. So you see here, it's very much based on randomness. So the selection of the moves, there is no exploration of the neighborhood, but just drawing a random move. So no steepest descent strategy, but selecting a random move. We compute the delta. So the delta is the function in the state S plus M. So with this notation, we mean the state obtained applying the move M to the state S, minus the cost function in the state where we are now. So if delta is less or equal than 0, here I'm assuming we are talking about minimization problems. So in minimization problems, delta less or equal than 0 means either a good move, an improving move, or a sideways move. So improving and sideways moves are always accepted. So what it means that S plus M becomes the new state. So we copy S plus M in S, And then we also ask ourselves if we are improved on the current best solution. If delta is not smaller or equal than 0, this means this is a worsening move, but sometimes we do accept worsening moves. Okay, so that's one of the ways to overcome the issue of local minima. So sometimes we accept worsening in order to escape from local minima. Okay, so if so this is the, we draw a random number from 0 and 1. So if this is less than e to the minus delta divided by t, we accept the move. In other words, we accept the move with a probability which is proportional to delta divided, which is related, let's say, to delta divided by t. So in simpler words, the larger is the delta, the smaller is the probability that we accept the move. So this means that we accept move which is small decrease, small worsening. We accept a very low probability a move with a large worsening. We respect the temperature is below. So this means that the higher the temperature, the more the higher the probability that we accept around a worsening move. So let's say the metaphor is this: when the temperature is high, the system accepts a lot of moves. So it's like the cooling of the metals, that in the beginning, when the metal is it's very hot, molecules move everywhere. When slowly the temperature goes down, the molecules tend to do not move anymore and stop in the best structure. Okay, so this is what is called the Metropolis acceptance criterion. So, and the simultaneous is based on the Metropolis acceptance criterion. Okay, so here obviously we don't have to check whether we have to update as best, because we are worsening, so it cannot be. Okay, when we have finished the number of iterations at the given temperature, we decrease the temperature. This is done by T becomes T multiplied by alpha. Alpha is a factor which is smaller than 1, so alpha is normally 0.9, 0.99, and so on. So the temperature goes slowly down, and when the temperature is very, very low, basically we don't accept any more worsening move, and basically we are doing some sort of descent, only descent strategy. Okay, so let's now analyze this simultaneous annealing idea. Obviously, there are some decisions which are completely problem dependent. So, which is the search space, which is the neighborhood relation, which is the cost function. So, obviously, these are the most important ones, I would say. But obviously, there's not much to say in the general terms, because we cannot, speak about them. So these really are based on the problem. In particular, the most important one, we know everybody who works on local search is the neighborhood relation, okay? But if the neighborhood relation is problem dependent. So here we will discuss when we discuss applications. Okay, but now let's move on the problem independent components. So there are various choices made here in the definition of simultaneity, which have been questioned by many researchers. And so we want to identify them and see which are the possible variants in order to improve the quality. The first one is the initial temperature. So there are various ways to decide which is the initial temperature. This is the fixed value. So we just have a parameter, but there are other options to start the initial temperature. Then there is the stop criterion. This also can be changed. So it's not that we reach given final temperature, but also some other options like quality. There are many number of accepted moves and so on. Then there is the length of each temperature. This is fixed. So in the basic simultaneity, this is a fixed length. But obviously there are other options in which can be longer in the beginning, shorter in the beginning, longer at the end, and so on. The exploration criterion. So here we say, okay, we draw a random move, but there are other options. The acceptance criterion. So the acceptance, as I said, this is called Metropolis. Here, this is the most studied one. So the acceptance criterion, there are a lot of proposals to have a different acceptance criterion to improve simulated annealing. And the last one is the cooling scheme. And here I put two options. So I mean, the cooling scheme, but also the reheating. So sometimes you say, okay, now I'm stuck in some sort of local minimum. Let's restart in a way, but not a full restart. So we stay in the current solution, but we reheat the system. So the temperature is put back to some high value, which not necessarily the initial value. So there are all these possibilities. There is a beautiful work by Alberto Franzin and Thomas Tutzler. By the way, Alberto is here listening, so if you want to ask questions to him, feel free, if he will be till the end. So what they did is they collected all the possible options, at least the most important, the one in the literature. So you see, for any of these 7 choice points, they collected several options, okay? So here, I know most of them, but I must say not all of them. Some are, well, I don't want to go into details of this. As you see, some of them are not called simulated annealing. For example, threshold acceptance, great deluge, late acceptance climb. These are variants that have their own name. So, but we recognize them as variants of simulated annealing, okay? So if you see, if you want to compute all possible combinations in order to say, okay, which is the combination which is best, obviously it's computationally impossible, because you should have to test 8 times 9 times 16 times 9 times 11 and so on, okay? So really it's a huge combination of possible selection. So I would say it's hopeless to say that for every problem we test all possible variants. So there should be some guidelines that we will discuss now. Okay, so some comments on the work by Franzin and Stutzle. So there is a large number of combinations, as I said, and not only large number of combinations, but each combination has its own parameters. So of course, if you say, okay, the combination is the basic one, the one we have seen, then you have to tune the parameters like T0, TF, and so on. So really, the number of trial runs that one should do, it's extremely large if one wants to have a full picture of which is the best, let's say, best in quotes, configuration. So as I said, when you compare configurations, obviously you have to do it in a statistically principled way, okay? But obviously this is intractable. So, I mean, it's not enough to just compare the average value on some instances, which is what people used to do, at least in the early stages. In fact, here I have a warning. So you should be suspicious of early comparison results. So if you see an old paper and you say, okay, this combination is better than that one, at that time, maybe there was not the culture of using statistical tests to say, okay, this is not by chance, but this is really, we can discard the one combinations with respect to the other one. Okay, so in the paper that I also advise you to read, as I mentioned, the paper I mentioned before by Franzin and Stutzle, there is a general idea that the most important ones are the exploration and the acceptance criteria out of these 7 possible hotspots to change. But also that it is hard to draw conclusions across different problems and data sets. Not only different problems, also different data sets. Okay, so that's the picture in which we move. But I want to add something that in my experience, so this is an extremely interesting work that I really appreciated, but I think there are other issues that should be taken into account. And in particular, these are those that I call the semi-dependent components. So there are some general issues which are, as I said, in between problem dependent and problem independent, like the 7 ones we have discussed so far. So first of all, the initial solution strategy. So should it be random? Should it be something different? So now in the next slide, I will discuss it in more details. Also the neighborhood composition, because normally when we do local search, we have many neighborhoods. So it's not just one neighborhood. So when we do, for example, travel sensor, you have 2-opt, insert, 3-opt, there are many neighbors. So how do we combine the different neighbors? And the third one, it's how we aggregate the cost, because this is, I think it's mostly neglected, but I think it's crucial, at least in my experience, that how you aggregate the cost of the various components of the cost function. Because mainly the issue is whether when you have some sort of distance to feasibility, then you have to take it into account together along with the cost, the objective function. Okay, so let's see this in more details. First of all, as I said, the initial solution, should it be random? Should it be greedy? Should it be some other sort of heuristic? This is obviously problem dependent, because I mean, you cannot say, okay, it should be greedy, but which greedy? How much time, how long should I invest, how much time should I invest in the initial solution? Also, as I said before, there is the neighborhood composition. So assuming that you have many neighborhoods, what do? You do the union of the neighbors, you do in sequence. So you do one run with one neighborhood and then another run with another neighborhood. So these are issues that should be put into the big picture. Obviously, these issues are not in any problem. Some problems have a very natural single neighborhood, so there is no discussion, or some problems have no easy, greedy initial solution. So this is kind of, as I said, semi-dependent. And then the cost aggregation. As I said here, there are two main approaches. The one-stage approach, in which we basically create a cost function, which is a weighted sum of the distance to feasibility. So this red component is the distance to feasibility plus the objective function. This WH is a parameter that you have to add to the set of parameters. Okay, so normally double H should be big enough so that the feasibility is preferred to quality, but also if it's too high, then you have to remember that you compare the delta with the temperature. So if it's too high, then maybe you never do a worsening move in terms of distance to feasibility. So these two should be at the same level in some way. So these two components, WH, TDF, and objective, should be some sort at the same level, but with the first one slightly more important. Or the most usual approach is a two-stage approach, in which first people solve the feasibility problem, if there is a feasibility problem. Of course, many problems don't have this feasibility problem. So many problems, any solution is feasible. If you think about travel salesman again, in travel salesman, any solution is feasible. So you don't have this issue of one stage, two stage. And the stage two is to solve the optimization problem, but never violating the distance to feasibility. So never going to an infeasible solution. Okay, so the idea is that any move that leads to an infeasible solution is discarded. So it's not considered, so it's not even drawn. So when you do a random move, you draw a move that is feasible. So obviously, we cannot do this from the beginning, because from the beginning we have a lot of infeasibility. So obviously we have to take care of them. But at the point in which we get to a feasible solution, we can say, okay, we never go back to infeasibility, and we keep on only, we consider when drawing the random move only feasible ones. Okay, so after this view, I want to say which is my favorite configuration of simulated annealing. Obviously, I say favorite in quotes because I just said there is no favorite, so you have to test all of them, okay? But then I say, okay, this is my experience. So I also said that testing all of them, it's impossible, so you have to start with something. So this is my view of what worked best in the past in my experience. Okay, first of all, I am very fond of the bounded, of the cutoff mechanism. This is a very old idea, and it's we can see the code. So the idea is that we decrease the temperature, not only when we reach a certain number of iterations, but also when we reach a certain number of accepted moves. Okay, so we have this new counter, which is n with a, and then we update n with a when we actually do a move. So in these two cases in which either a move is improving or sideways, or the move is done because of the random selection. Okay, so the idea is that if we have done enough moves at a certain temperature, okay, that's enough. So, and this speeds up the initial stage, because at the initial stage we do a lot of moves, very random. So, I mean, there is no reason to stay that long in a certain time. So the idea is that at a high temperature we should shake the solution. So once the solution is shaken enough, we can stop. Okay, so that's the one thing that I would always add to your basic simulated annealing.
There's a question from the audience, which is related to this, like the bounded temperature length. The question is, why do we even have this bounded temperature length? Why don't we just decrease the temperature in every iteration? So why do we stay with some temperature a certain number of iterations?
Okay, if you say, okay, I decrease the temperature every iteration, this can also be done. Okay, so you have a much closer to one cooling rate, and then you decrease it every time. This is also can also be done, but the reason for not, so you have, instead of having certain steps which you go down, you basically you make it a slope. Okay, instead of having steps. Okay, the initial idea was that we should have these steps. So the initial idea with the metaphor said we should have these steps. I agree that maybe these steps are not necessary, but this cutoff, it's the reason to get back to the steps, because this cutoff make that you do steps, but you want to do some of them shorter. Okay, so if you don't have this, if you decrease it any iteration, there is no reason to. This cutoff mechanism does not apply, because basically you decrease it every iteration. Instead, you want to say, okay, I do a big decrease, but then I control the length of the temperature. Okay, so I want to do it. So that's basically my intuition. The reason why we have these steps from the very beginning, you should ask the authors, but my intuition is this one. So if you have steps, then you control the length of the step. If you have atomic steps, you cannot control it. Okay.
But as an alternative, we could, like, every state we reduce the temperature, but only by a smaller amount.
Okay, that's another option. Okay, so you say I work on the cooling rate. So I decide if the move is accepted, I do a different rate. That's also possible. Yes. Okay, that's another option. Obviously, you should add it to the big picture as an option, and then test it. Okay, so. So my other favorite idea is that you should always work on iteration-based stop criteria. Why? Because otherwise it's incomparable. So I see many papers very annoying, which say, okay, with this configuration of the parameters, I get this solution, but with 1 hour. With the other configuration of parameter, I get this solution, which is worse, but it takes 5 minutes. So I don't want to compare. So how can you say what is best? So long with a better solution, or short with a worse solution. So I think that if you want to compare the parameters, you should say you should fix the iteration, the number of iterations, which roughly is the length of the is the time, the length of the search. So the total number of iterations is capital I. Which, as I said, corresponds to fixed time approximately. And so what we do, we fix the other, we remove one parameter, which we remove ns, and s is based on I, okay? So this is a simple mathematics in which once you have decided at the value of I, which say, okay, I want to do 10 million iterations, then I know how many iterations I want to do at every temperature. It's based on how many temperatures I have. So this is a simple mathematics. And then NA is fixed with a ratio of NS. Okay, that's my way to go on. Let's see other things. So initial solution, always random. So trying to start from a good solution always, most of the time traps the search in some local minimum. So I don't spend effort, human effort, and computational time to some smart initial solution. The neighbor composition, in my view, the best is always the union. So basically you say, okay, I draw a random move in the union of the neighborhoods, but with non-uniform neighborhood selection. So I fix some probabilities and say, okay, I make a weighted draw of which neighborhood I want to select from, and then I select uniformly inside the neighborhood. Obviously, these are other parameters, so we have additional parameters to tune. And for the cost aggregation, my experience is the best is to use one stage. So some R constraints are left outside the search space because these are useless. So if there is one unavailable spot, then there is no point to put something in an available spot. We just never do it. But others like conflicts should be in the search space, and this so what I call the one stage approach. So that's my favorite one. And obviously this W capital H is an additional parameter. So we have more parameters to tune, not only the basic ones of simulated annealing, temperature, cooling rate, and so on, but also new ones. Okay, obviously, as I said, we need to do some parameter tuning. So the way to do parameter tuning is to fix the number of iterations. We have all these parameters, T0, TF, alpha, sigma, all the rows, which are the probability of each neighborhood. Obviously, one of them is related to the others because they have sum up to 1, and the weight of the R constraints. And then what we do, we use this Hammersley point set. So the parameter space is sampled using the Hammersley point set. So this is a very old idea, but very nice, I believe. So I'll give you an example. So here you have on the top, the full factorial with 1,000 points in 3-dimensional full factorial. You see, this is 1,000 points. You see the projection in the various phases. And this is 100 Hammersley points, okay? You see the projections are very similar. So with 100 points, basically we cover roughly all possibilities. So there is no reason to use all the full factorial points. Okay, so and the nice thing of Hammersley's point set is it's totally scalable. So any number of parameters, any number of points, you get the configurations. Then we use F-rays by Birattari and others. So the idea of F-rays here, I stole the slide from Thomas Stutzle that he gave in a conference in Udine that we invited him. So basically you have a certain number of configurations. You run all the configurations for a certain time. So we start with initial set of candidates, and then you run them on new streams, new instances anytime. But at some point you can say, okay, this configuration is worse. So as soon as you get enough evidence that this configuration is worse, you stop it. So this red part is the part that you save, the time that you save. So you don't have to do, you don't run the fixed number of instances, a fixed number on all configurations. You save time, and you can use this time to go on with this race. Okay, so it's a race. At certain point, there is one winner. If there is no one winner, means that they are not distinguishable statistically. Okay. Then we use this is inside F-race. So inside F-race, you use the Friedman rank sum test, the Wilcoxon test to say if there is a statistical significance. One is used when there are 2 candidates. One is used when there are many. And we use this software tool, which is called JSON to run, which is a software tool that does all these things. So it selects the Hammersley points, run the F-rays, and so on. So it's a very useful software tool. Okay, so there are some open issues which are still open that I'm not discussing here, where you can do feature-based tuning. So you can say not fix the parameter based on some function of the features of the instance. So you can say density of the graph or other measure of this. You can say, okay, if the density is high, you should start with a higher temper or things like that. And also to do online or adaptive tuning. So you can change the tuning during the search. Some of the parameters can be done. Okay, so we use this idea on many applications. So these are my list of applications. So most of them are educational timetable because I'm a fan of this problem. So I've been working on many timetabling problems, but also other problems, okay? So today I think I have time only for one application. So I selected my favorite problem, which is the curriculum-based course timetabling, because I kind of invented this problem. So the instances come from our University of Udine. Actually, somebody called this problem the Udine timetabling, so I'm very proud. I don't do it because I don't want to be presumptuous, but some people call this problem the Udine timetabling. So, so I really want to talk about my problem, but these are not the best results, I would say, of our ideas, but I like to talk about this problem. Okay, these are some of the papers that we wrote. So I show them not to show off, but to recognize the work of my co-authors, in particular the two members of my research group that are highlighted here. So Sarah and Luca, I think they're here. So thanks, Sarah and Luca. You see there is also Nusret Musli, which is the organizer of the conference. That's why we are connected. That's why he invited me. So I hope we can write more papers together in the future. Okay, so let's talk very briefly about the curriculum-based course timetabling. So we have courses and lectures. So for example, the course databases should be taught 3 times a week. So we are doing the weekly timetable. Then we have periods and days. So we have a certain number of periods that are divided in days. So for example, here we have 5 days, 5 periods, 5 slots per day, so 25 periods altogether. We have rooms with a number of seats, and then we have the curricula. In fact, this is called curriculum-based course timetable because so the conflicts are given by curricula, not by enrollments. Okay, so the other options are the enrollment-based. This is curriculum-based. So for example, civil engineering second year, they do math 2, structural engineering, and so on. So this creates, this curricula create conflicts, but also other soft constraints, because we want to the timetable to be as compact as possible for the students of each curriculum. Mechanical engineering, and so on. As I said, no student enrollment maths. Okay, I'll try to go very fast because I see that I have very few minutes, right? So I'll try to go fast. So we have conflicts, curriculum, room occupancy. Room can be occupied twice. Teacher availability. Room capacity is soft because obviously the room has 100 seats and there are 101 students. We always we don't prohibit that, but we accept it because it's the number of students is always overrated. Minimum number of working days for each course, so kind of compact courses in a few days. Compactness and so on. Okay, room stability, don't want to change room and so on. Okay, this was used in a timetabling competition. This is a kind of simplified version, but instances are real. Okay, so as a search space, we use the matrix courses time periods. So, and the value is the room. Okay, so this is given room number 1. All these lines means there's a 0. Okay, teacher availability are never violated. As I said, some of the hard constraints are never violated, others are. So for example, conflict violations are possible. So for example, if course 1 and course 3 are in the same curriculum, this is a violation. Room occupancy, here you see a violation. R1, it's a violation because it's used twice in the same period, and so on. Okay, neighborhoods, you can move a single lecture, but you can also swap 2 lectures. Okay, so you move 1 lecture in a new period in your room, but swap 2 lectures in the rooms and period. Of course, we use simulated annealing. The parameters are the ones we have mentioned, so nothing new to say. There is a ratio, as I said, this row parameters here, there is just one, which is the ratio of selecting move lectures and swap lectures, and there is the weight of the hard constraints. Okay, well, some preliminary analysis identified these 2 as the most important parameters. we use both Hammersley point set, but also this other configuration of the search space, which is the near orthogonal lighting hypercubes by Choppa and Lucas, because this is another option. It's a, let's say, competitor of the Hammersley point set. The problem with this hypercube is that they work only for certain number of parameters, certain number of points. So you cannot select the number of points that you want. You have to do which mainly 2 to the n minus 1. We use race. The validation, there is a website that unfortunately now it's under maintenance, so it's not usable, in which we have all the results with also the validation. So if you upload your solution, this is validated. And these are the results. So you see the results at that time, okay? So this is not the newest application. That time we had a very good results. So we had so all the blue are the best compared with the best one at that time. Okay, so we had a very good result. Other problems still have very good results. So it's very, okay. So I go to the conclusions. So simulated annealing, let's say it's a simple and old-fashioned technique, but outperforms many modern ideas. So as I said, I share the idea of Sorensen that we should go back to the basic components and see what we can do with that, and then why something works. So I don't want to invent a new neighborhood, a new meta-heuristic and say this is good. So I really want to stick to show what I can do with the known ones. Obviously, different configurations need to be explored. I add without ideological bias, because this is very difficult to not try to favor your best candidate, okay, your best horse. So this parameter tuning is crucial, as I said. And unfortunately, there is no standard software tool for simulated annealing and local search in general compared to Cplex or others. So this is obviously one of the, maybe because it's not that difficult to implement it from scratch, but I think there should be some sort, we should work on this point to get a better, to improve the situation on this point. Okay, I hope I've been in time, because exactly 40 minutes. So thank you for your attention. I'm open to questions. You can ask questions also to Alberto Franzini, as I said, he's here. So, but please.
Mm-hmm. Okay, great. Thank you. Thank you for the talk.
Thank you.
Now we're going to do the Q&A. So very brief. So we have already a few questions in the chat. So one question is regarding what kind of moves can we select during in our neighborhoods. So here David Bernal is referring to for the moves that we take. Are we assuming that they all guarantee ergodicity, which in this case means ergodicity, which it seems that it means that from using just those moves we can go to any state of the problem.
Yes. Mm-hmm.
So are we concerned with only those kind of moves, or we can take any move that we use?
Okay. Obviously, you need that the search space is connected under your neighborhood. Okay. Mm-hmm. Otherwise, it doesn't make sense. So that's the main issue that let's say the main criterion that. But this is quite easy most of the time. So especially if you use a composite one. So I mean, there are cases in which the search space is not connected. It's easy to prove that you can go from any state to any state. So in the cases I never had this problem, okay, that you can prove easily that you can go from any state to any state. And selections done as uniformly as possible within the single neighborhood, if this was the question. Mm-hmm. Whereas it's done weighted between the components. Is that?
Okay, I think that's a good answer. And we have some other questions by Tatiana, asking, why do you prefer F-race over some other, for example,
okay.
I-race or SPO?
Okay, the easy answer is laziness. Okay, I'm familiar with that. I'm not going to say. But let's say I would say that I-race and SMAC and others are more when you're doing some. You are kind of blind, you have a kind of a black box, okay? So you don't know what they do, so you really have no idea what to do, so you want to use some automatic tool to do it, okay? But if you have a lot of insight, I think some low-level idea like F-race, so I don't want to leave to the tool to do the machine. So this I-race is the idea is that they make more automatically. This is done for the, let's say, naive user. I don't consider myself a naive user. I want to take control. So what iRace does automatically, I want to decide myself how to do it. So I like to use this more basic tool, which is FRAs, but I understand that in many cases you prefer to use something more more elaborate. So you want it to do it for you, because if you're using Cplex with 100 parameters, you don't have idea what's going on. So you really want to have something automatic, okay? But here I want to take control. I don't want to leave the control to the tool. That's, let's say, the answer.
Okay. And here we have like one question. So we have two questions, which I will merge into one just for the interest of time. So we have Ronald Yap and David asking about local search or simulated annealing for set problems or mixed integer or general mixed integer programs. So would those local search techniques be competitive for those kind of paradigms? Is local search appropriate for those kind of paradigms?
Okay, for SAT, I mean, the early good algorithms for SAT in the 90s by Bart Selman and I don't remember the name of the other one, they were local search. So the initial the initial rise of SAT as a lingua franca for translating everything to SAT was done because of local search methods. Now, I'm not an expert of SAT, but now I can tell it's not true anymore, okay? So there are better algorithms for SAT, which are not local search based, okay? But I'm not the expert. Concerning mixed integer programming, yes, of course. I mean, I think you can use local search for mixed integer programming problems. My experience is that now I always try to write something using Cplex, because I don't want to say, okay, my local search is very good, and then later discover that this is easy and solve to exactly with Cplex without any. So I do my naive implementation of Cplex, and I compare it. Obviously, you can say, well, you're comparing in the straw man, because if you're not good in implementing in creating a model, well, but at least I want to compare with a straw man. And my experience is that local search goes far beyond the basic implementation of mixed MIP tools. Obviously, somebody expert of MIP tools can come with some smart encoding, cutting, and column generation, and so on. They can improve it, of course.
Great. So the audience thanks you for your answers.
Thank you.
And we also thank Professor Schaerf for this great presentation. And now we will go to the second part of the talk by Professor Raidl Günther. So I already introduced Raidl Günther, but maybe it makes sense to do this again after 45 minutes. It's just Professor Raidl Günther is a professor at TU Wien in Austria, and his main research interests are in data structures, algorithms, and in general combinatorial optimization, with a focus on metaheuristics, mathematical programming, and the combination of these two things. Now today he will talk about how to learn these metaheuristics automatically, so using reinforcement learning. Okay, so please.
Okay, hello, and thanks for giving me the opportunity to speak here. So when I was asked to give a talk about recent trends in metaheuristics, for me it was immediately clear that the aspect of learning had probably the most influence in the field of metaheuristics in the recent years, and therefore I want to talk a little bit about this topic. So machine learning and metaheuristics have much in common. Yeah, so they are strongly related, obviously. For example, heuristics are what drives actually modern machine learning. Neural networks are trained with stochastic gradient descent methods, etc. But we want to focus here on the other side. So how metaheuristics for solving combinatorial optimization problems may benefit by utilizing modern machine learning techniques. But before starting with modern machine learning techniques, let me stress that the basic idea of learning in metaheuristics is absolutely not true or not new, because several of the classical metaheuristics already involve learning aspects. So give me a few examples. Andrea has already mentioned that in simulated annealing and other local search-based approaches, frequently not just one neighborhood is used, but several neighborhood structures are used in combination. And there is the question, of course, which neighborhood should be used when and with which probability maybe, or in which order. And self-adaptive approaches exist there. So to automatically tune the operator's application probabilities, yeah, and order maybe. So this is based on observations, how well they perform over the search, over the heuristic search, and those neighborhood structures or operators that are doing well get an increased chance of being applied again. And so the approach learns and adapts over the course of the heuristic search. Another good example are evolution strategies. I don't go here into details. These are more meta-heuristics targeted towards numerical continuous optimization problems. But the key idea there is that you have a solution and you mutate it by adding some Gaussian noise. And of course, the amount, the standard deviation of this Gaussian noise plays a very crucial role, and self-adaptive strategies are also applied there. So there is also this learning involved there. Another example is guided local search. That's maybe not a very prominent meta-heuristic, but a quite old one. And the idea is very simple. You perform a local search, and once you come into a local optimum, you penalize the objective function by adding an additional term in order to get out of this local optimum. So the solutions close to these optimal solutions are penalized. Yeah? And therefore, you can then continue your local search and get into the next local optimum, which is again penalized by adding a term. So in some sense, the objective function is learned here in this approach during the course of the meta-heuristic. Yeah, one other example is reactive taboo search. Taboo search is a method where memory is used to store attributes of already visited solutions in order to avoid visiting them again. And there, a very critical parameter is the length of the taboo list. And again, self-adaptive mechanisms are used there to get rid of the problem, what the ideal setting for this taboo length is. And last but not least, let me briefly speak about end colony optimization. So I have a slide here for those of you who have not heard about this meta-heuristic. So the key idea is very simple. Solutions are iteratively constructed by a randomized greedy algorithm, you can say. And the most important aspect is that these constructions are not independent, but we utilize some pheromone data structure, a table, and pheromone arrays frequently used here. And these pheromone values basically are values for possible variable value assignments. And when the pheromone value of a variable value assignment is larger, then this assignment is performed with a higher probability. When the pheromone value is lower, then the chance of doing this assignment is smaller. And yeah, during the course of the optimization, the better solutions are taken and their variable value assignments are used to update the pheromone table. And in this case, these good decisions are reinforced and other values are reduced. There's some kind of evaporation taking place. So that's the idea here in very few sentences of what end colony optimization does. And here again, this learning takes place. The pheromone matrix is immediately the memory storing the learned aspects, which are then used in the construction of the successive solutions. So learning is not new at all. Yeah, I want to mention one more heuristic here, where also learning is involved. This is Monte Carlo tree search. Maybe Monte Carlo tree search is not usually called a meta-heuristic for doing combinatorial optimization. actually it originates in playing board games, yeah, agents for board games like chess, Go, whatever. There it's a quite fundamental technique, but it can and already is already applied to several combinatorial optimization problems, and therefore I want to consider here in particular, since we will later on build on it. So let me briefly explain the main ideas behind Monte Carlo tree search. Let's consider some two-player board game like chess. And as the name says, it is a kind of tree search. So we build a tree node by node, and one node of this tree corresponds to a position of the game, yeah, the root node to the original position. And the successor nodes are basically those nodes which are those states which you obtain by playing a certain move, by taking a certain action. And yeah, these nodes in Monte Carlo tree search contain two important additional values, which are the number of visits, so how often this node has been visited, and the number of wins that have been obtained by going over this node, or by doing the action that led to this node. And yeah, during each major iteration of Monte Carlo tree search, these four phases are performed here. So in the selection phase, we always start at the root node and go towards a leaf node. And we do this by always selecting the successor node according to a specific rule. There are several different rules, but one of the more prominent ones is the upper confidence bound on trees. And I've shown you this rule here. Basically, it says that we consider this number of wins and number of visits, and the first term prefers nodes with a larger win rate. Yeah? So this is taken, so the number of wins is taken into consideration divided by the number how often the node has been visited. And the second term considers the number of visits of this successor node J in relation to the overall number of visits of the parent node I. So nodes with less visits are preferred here, get more attention in the future. And C is a constant that balances these two terms. So this first term takes place of exploitation. So nodes that, by which we have observed more wins are taken more frequently, but the other term, the second term, considers the exploration aspect that we do not neglect other nodes, and by the parameter C you can balance these two aspects. Yeah, so this is the selection phase. And what is done next when we have reached such a leaf node? Yeah, this node is expanded, so we create one successor node, a new leaf node, and then evaluate this node. And this this new node is evaluated in the simplest form of Monte Carlo tree search just by playing a naive random game. So doing a rollout, a random rollout as it is called. Yeah, so really just very naively and quickly playing a game, always selecting some random move. So in this way, we have here a strategy that really doesn't use any problem-specific knowledge, but of course, usually you will be able to improve it by incorporating a certain problem knowledge, for example, by applying some heuristics in these random rollouts. But in this way, we obtain finally, either we obtain the knowledge whether this path leads to a win or a draw or a lose, and this information is then used to update this win and visit values in the nodes of this tree. Yeah, so all the visit counters are increased and the win counters are increased for the white player here because white has won. And yeah, this is iterated many times. And yeah, as I said, for many board games, this works quite well and has been adapted to also work for solving certain combinatorial optimization problems. Yeah, for example, the multiple sequence alignment problem is one that has been addressed in this way. But usually these are extended versions that also incorporate some problem-specific knowledge to really be competitive. But that's the basic principle of Monte Carlo tree search. And what you can really see here is this learning aspect. So without any problem-specific knowledge, we still have here this aspect that the paths that lead to wins are reinforced by increasing the respective values, and the search therefore focuses more and more on this more promising parts, but does not neglect also other paths and other parts of the tree search by the second term of this UCT formula. So that's Monte Carlo tree search. And yeah, before going more into details of reinforcement learning, let me very briefly give you a general classifications and idea of where machine learning techniques have already been applied in conjunction with metaheuristics. So this is really a very wide field, and many ideas have popped up in the recent years. And El Ghazali Talbi published a nice paper, Machine Learning in Metaheuristics, from which I've stolen here also this figure, and I briefly want to discuss here with you the classification he does. So basically he distinguishes between problem level data-driven metaheuristics, where the metaheuristic actually addresses the problem to be solved in some way, but is not so much included in the meta-heuristic directly. Then the low-level data-driven meta-heuristics, where the machine learning component is used, for example, we will later see, I will discuss this. And then we have the high-level data-driven meta-heuristics. So let's consider this in a bit more detail. Problem-level data-driven meta-heuristics include, for example, in the simplest case, landscape analysis, from which you can draw certain conclusions and design, for example, variation operators in a better way. Objective function. Yeah, there are many approaches that try to approximate an objective function. So consider some problems where it's very difficult to come up with a closed form expression for the objective function, or where calculating this objective function is very expensive. Yeah? For example, problems in design of wing shapes or something like that, what you usually have to do there is to perform expensive simulations. And there it makes sense to try to approximate the objective function by some knowledge you have already gained from similar solutions that have been evaluated. And in this way, an approximation of the objective function can be learned together with the model that is actually used to approximate the objective function. So there are interesting combinations where approximating the objective function is included in the process of solving the problem. Gaussian processes are, for example, one technique that are frequently used here to determine the most promising, most interesting next solution candidates which should be evaluated. Similarly, it's sometimes hard to express the constraints of a problem in a simple form by classical mathematical constraints, and also constraints can be learned and have been learned. In conjunction with constraints, an additional aspect is also how to deal with them. And the classical ways in metaheuristics to deal with constraints is either to penalize them in the objective function, but then also the question arises which penalization term is best suited. Yeah? So if penalization is too weak, then you get too many infeasible solutions in the end. If it's too strong, then maybe you do not really exploit slightly infeasible solutions that may lead you into areas of the search space where good feasible solutions can be found. So this penalty term can also be learned during the optimization. Or the other techniques are repair strategies. Yeah? And again, the question arises, how can we most meaningfully repair an infeasible solution? And again, machine learning techniques have been applied here. Yeah, last but not least, problem decomposition. Of course, when you are confronted with a huge problem instance, one possibility is that you try to decompose these problems in smaller subproblems which you solve independently, and then to somehow combine the solutions. And classical clustering techniques, for example, can here be used and have been used to find most meaningful problem decomposition, to make this decomposition approach most efficient. Yeah. Then low-level data-driven meta-heuristics. Here, basically all those techniques, these classical heuristics I mentioned at the beginning, are examples. Yeah, so where this self-adaptive tuning of parameters takes place, but also when you create initial solutions, maybe in a more meaningful way, machine learning techniques can be used. And yeah, the selection of variation operators, as I said, in variable neighborhood search, in adaptive large neighborhood search, this application probabilities, this falls into this category of low-level data-driven meta-heuristics. Yeah, and then we have this so-called high-level data-driven methods, and this is really a research area on its own. I have here another slide for this. The term there is automated algorithm selection or automated algorithm configuration. And the idea here is that frequently you have not just one available algorithm to solve a problem, but you have a couple of such algorithms with very different characteristics. And maybe there is not a single algorithm that dominates all the other algorithms. In such cases, automated algorithm selection may make very much sense. And basically this means that you try to train a classifier based on certain characteristics of the problem. So you define features of the problems that you use as input into a classifier, and the classifier yields you then a recommendation for the algorithm that should be most promising for a particular problem instance at hand. Yeah, the good question, of course, is which features to use, and this is, of course, also very problem specific. But for example, for graph problems, there are typically features like, of course, the number of nodes, the number of edges, maybe the density of the graph, the many more aspects of the structure of the graph, the tree width maybe. Such features can tell you a lot when used in such a classifier, and give you well-working recommendations which algorithm might perform best in which case. By the way, our host here, Nusret Musliu, is an expert in this field and has done considerable work here on automated algorithm selection and also configuration. This brings me to the second approach. It's more or less a generalization where you do not just select one algorithm out of a portfolio, but you want to create or configure an algorithm by selecting individual components. Yeah? For example, when you consider a variable neighborhood search approach and you have several different neighborhood structures and algorithms for searching them, such an algorithm might provide you the subset of most meaningful neighborhood structures that in combination should work best for the problem instance at hand. So this research is a research field basically on its own. And yeah, now I would want to get in particular to reinforcement learning and combinations of metaheuristics with reinforcement learning. And for those who have not heard of reinforcement learning so much, let me briefly address the general setting, which is usually considered here. So reinforcement learning is a subdiscipline of machine learning, and the environment, what we consider here, this setting shown in this figure. So basically, we want to train an agent, that's our algorithm, that acts in a certain environment. And the environment can be a maze like shown here, or can be a computer game, or can be a Go, or can be a physical control task, yeah, difficult one in which you have to control certain parameters in order to get some behavior. So this can be very different. And the key idea is that the agent observes the current state in some way, so gets some input data on the current state. And based on this input data, he has to act and selects one of the available actions. So maybe in a maze, he can go forward or to the right, but not to the left because there is a wall, and selects one action, and this creates a new state. And this new state is again observed by the agent, and occasionally the agent also receives some reward. It may happen that reward is only received at the very end when the agent has for example, found the exit. Then, yeah, only then some reward is paid, and otherwise the reward is zero. But it can also happen that some intermediate reward is obtained. It really depends on how the environment is defined here. And yeah, this whole reinforcement learning area has received much attention in the recent years, in particular due to DeepMind's successes in playing Go and chess and several other board games. Yeah, I'm sure most of you remind in 2017 when Google, so DeepMind's daughter of Google, yeah, with much advertisement, let their agent play again against Lee Sedol, and also won this tournament. Of course, this is a very different setting. We are interested here in solving combinatorial optimization problems, but this principle of acting in an environment until a certain final state is achieved, this can also be used in order to solve combinatorial optimization problems. Yeah, in fact, when you consider any greedy construction process, yeah, there you also make some observations in which you have your greedy function and then decide how to act, and this yields then a new state, and step by step you assign values to your variables and construct a solution in this sense. And therefore we may consider to more or less directly apply these reinforcement learning agents also to solve combinatorial optimization problems. Let me very briefly sketch how one quite prominent reinforcement learning technique works, on which several of the more modern are also based, and that's Q-learning. Yeah, that's really not a new approach, but one of the more fundamental ones. And of course, the overall goal of the agent we want to train here is so that actions are selected so that the rewards of all the forthcoming steps are maximized. Yeah? And Q-learning considered more specifically so-called Q values for state action pairs. And they should approximate the weighted expected sum of rewards to receive from a state S onwards when applying the action A. Yeah, so for state action combinations, we have these Q values that we want to learn. And yeah, when you have these QSA values, then of course you can, for a current state, check out all the possible actions and compare the Q values and maybe take in a greedy fashion the action with the highest Q value. That's the basic idea. And learning these Q values is actually done in a relatively simple way by considering a larger amount of data, of episodes, so to say, that has been played, and updating initially randomly set values by a formula like this. And yeah, basically these updates are performed by adjusting the current old value of the Q, of the Q value of state action pair ST by a temporal difference value. And this temporal difference value is nothing else than the reward that is immediately received for doing the action, for performing the action AT, yeah? Plus we add here the estimate of the optimal future values by considering the Q values of the state we receive, or which we get by performing action AT. And there again, we have, of course, many possible actions, and there we consider, we take the best one. Yeah? We assume that the best action is again selected here. And that's then the maximum of the Q values of the successor state. This is taken into account, and the difference is determined to the old value. And yeah, by this value essentially multiplied by learning rate, this current old value, Q value, is updated. This discount factor, by the way, is just used to give rewards that are expected in the near future, higher values than rewards that are expected to be received later, but this can also be set to 1 in many applications. So that's the very basic idea. By such a simple update rule and we are performing iterations for iterations and taking the outcome and the performed episode and training the Q table here, this learning takes place. And maybe the whole approach reminds you on what I have told you about ant colony optimization. There we had this pheromone matrix, and the details were different. Yeah, nobody or not many would agree that this really are the same algorithms, but the spirit of the approaches are quite similar. Yeah, you have these data structures for variable value assignments, where you basically reinforce actions that led to good outcomes, while other values get decreasing values. Yeah, so that's Q learning. And one problem with classical Q learning is often that the state space is too large to have really an explicit table here for all possible states and all possible actions. And what is then done, and in particular done in the most recent reinforcement learning agents that became so popular, is that this table is approximated by a neural network, and this is then frequently called deep Q network, or DQN. Yeah? This original DQN was quite successful in playing Atari games. There the observations were really the screenshots, and yeah, the DQN basically then provided the actions that should take place to play this Atari game. Yeah, so that's deep Q networks. There are many variants of those kind, fancy abbreviations, as you can see here. I can't go here into details, just so much they differ in the state spaces, whether they can be discrete or continuous action spaces, whether they are on policy or off policy, meaning on policy means that they can only learn by data that have been obtained by applying the strategy of the reinforcement learning agent immediately, and off policy can also learn or agents that can also be trained by means of data obtained in some other fashion. Yeah, and now let's consider certain graph problems, and the idea here is to learn on many different instances of some related relevant type, to learn, to learn and to obtain some heuristic that is then applied to a new problem instance, and hopefully, yeah, when this works out, then we should get also a nice result here. So it's a kind of transfer learning that we want to consider here, where on different instances of similar type, the agent is trained and then applied to a new instance. And there are a couple of nice papers, and I focus here just on graph problems because I have to restrict myself in some way. And for example, Dai and colleagues did this. They applied such a deep Q network to solve with one and the same algorithm classical problems and graphs, namely the minimum vertex count problem, maximum cut problem, and the TSP. And noteworthy here is how they dealt with the different graphs. Yeah, of course, it shouldn't work just for one type of graph with one size, but they trained a more general agent that worked with different sizes of graphs, different structured graphs. And what they used here was a graph neural network. That's actually also a research topic on its own, just so much. Basically a graph neural network. They applied here more specifically structure to VEC. It's a particular kind of graph neural network, but the general idea here is that such a neural network gets its input a graph and outputs essentially for every node a value or a vector of values that somehow characterize the node within how it is embedded in the whole graph. Yeah? So these obtained values for the nodes do not just represent individual aspects in isolated fashion for the nodes, but somehow also the neighborhood of this particular node, how the node is embedded, what its neighbors are, and these aspects are reflected by this graph embedding. And here in this approach, what is basically done is that we really just get one value for each node, which somehow, in essence, reflects the likelihood that this node appears in a solution. And yeah, the node is then just selected in a simple greedy fashion, and then we get the reduced network with the remaining still relevant nodes. And again, this graph embedding is determined, and step by step, one node is chosen after the other until we have obtained a complete solution. Yeah? So in principle, that's a very straightforward approach. Just this graph neural network is here the speciality, how we deal with the graphs as input. And as results, what they obtained is basically not an approach that is competitive to the state-of-the-art. That's clearly too difficult, in particular for the TSP, as we all know. But this overall approach of learning worked in the sense that really approaches were obtained that were superior to basic greedy heuristics and also basic metaheuristics involving local search. Yeah? So not overall competitive, but interesting results were here definitely obtained. And one group of researchers around Lee that built on these results, they extended the approach in several aspects. Yeah, most importantly, they applied some standard graph reduction techniques. They applied some local search at the very end. And this boosted the approach already quite significantly. But most importantly, what they did is that they trained the graph neural network to not just output a single probability map on the nodes, but multiple probability maps. And based on these multiple probability maps, they performed then a tree search. So you can say that this graph neural network guided the tree search here in some sense. And this approach was much better. I mean, it was, to be fair, applied to a different kind of problems here. So it was not directly possible to compare these approaches. But the authors claim here really that they obtained state-of-the-art results for certain classes of these very famous problems here. Yeah, another example here that builds on similar ideas comes from Mittal, and they focus in particular on scalability to really huge graphs with millions of nodes. And to achieve this scalability, they had to apply here certain important changes. So most notably, they apply a graph convolutional network just once at the very beginning to the original graph. Yeah, this is basically done in linear time, and you get this embedding, again, essentially telling you likelihoods for the individual nodes, how likely they are to appear in optimal solutions. And then, second step, the Q-learning is applied with a much simpler neural network here to come up with combinations of promising nodes that finally yield or represent the solution. And yeah, one key contribution was here that this whole loop in updating or in calculating the new embedding once some node has been selected to be included in the solution, this update and also the training is done in linear time. Yeah, this is here the main contribution. Okay, yeah. Now let me briefly deviate from these graph problems, and I want to tell you a few or the basic principles behind this AlphaGo, or an extended version is AlphaGo 0, by which DeepMind achieved this superhuman results with respect to Go. So the key idea here is really very simple, and in fact there also exists quite short implementations of the basic principle of this AlphaGo agent. So the learning is done by iterated self-play, and one self-play works by performing for the first move a Monte Carlo tree search, and this Monte Carlo tree search yields a policy, so a probability distribution for the possible actions, and one action is chosen, usually in a greedy way. And then for the second move, again, independent Monte Carlo tree search is performed, and again, one action is selected, and so on, until we have a state where it's clear who the winner is. And one key change in the Monte Carlo tree search is now that Silva and colleagues apply a deep neural network for evaluating the leaf nodes. Yeah, remember what I told you before in classical Monte Carlo tree search. Basically, for the leaf nodes, we do some random rollout, some naive strategy, or maybe guided by some problem-specific heuristic. Here, this step is replaced by a sophisticated deep neural network that outputs probability, so a policy, meaning probability for distribution for all the possibilities, and also a value indicating the probability to win. And this is used within each Monte Carlo tree search. Yeah? So that's the key aspect. And you can also say that the output of this neural network is boosted by means of the Monte Carlo tree search. Yeah? This Monte Carlo tree search, utilizing a neural network in the nodes for evaluation, yields substantially better results, or substantially more promising policy usually than when we would just apply the neural network. And yeah, of course, this neural network also needs to be trained. And how is this done? Now, basically, these self-play games are all locked in some replay buffer and then in a parallel process used to train the network. And basically actions from this replay buffer are selected more or less randomly. That's important for the learning also. And yeah, with the respective state of the board and this performed action and the known outcome of the game, the neural network is more or less trained in a similar way like in Q learning. And yeah, it's in my opinion fascinating to see that this self-learning works in this way. So there's also this combination of the tree search where the neural network is already used. Initially, the neural network, as usually, is initialized with just random values, so does not really make much sense. But over time, this learning works, and yeah, by this combination of Monte Carlo tree search, you can expect a better outcome. And the principle of this AlphaGo 0 has been applied by several researchers in the very recent years now to combinatorial optimization problems. And I just list here two approaches or two papers. AB and colleagues applied this again to some classical graph problems, mean vertex cover, max cut, max click. And yeah, of course, it also, the question is always which kind of neural network is used here. Again, we have to use some graph neural networks since we are dealing here with graphs as underlying data structure. And yeah, what they obtained are much better results than the first approach I've mentioned, the structure to vec deep Q networks. So here one can really see that this tree search boosted the performance substantially in comparison to the simpler deep Q network approach. And they claim to have reached for certain classes of this famous problem, also state-of-the-art results. Graph coloring was addressed by Huang and colleagues, and they again focused on extremely large graphs with millions of nodes, and to achieve this, again, a very special neural network architecture had to be used, but yeah, the overall principle is here the very same, that Monte Carlo tree search has been used in combination with the specific network for learning. Yeah, so let me conclude. Clearly, machine learning, this hype of the recent years has also hit the meta-heuristic field, this in a good as well as bad sense. So not all the approaches that apply machine learning are always very meaningful, but there are clearly some interesting methods that have been suggested, and in my opinion, these reinforcement learning techniques are particularly interesting because of two reasons. Yeah, the first reason is that they may reduce the effort of manually crafting and tuning heuristics. Yeah, the classic way, for example, in some heuristic search is to manually craft greedy criteria or some criteria in some way which nodes should be pursued next. And to some extent, reinforcement learning techniques may do this better, or at least may relieve you of some manual effort. And moreover, in comparison to other supervised learning tasks, the good aspect by reinforcement learning is that learning is possible here without having labeled data. So meaning that you do not need a larger set of benchmark instances with optimal solutions to train from. Yeah? That would be necessary when you apply some more classical supervised learning approach. Yeah. Also, I have to warn you that just naively taking one of these famous reinforcement learning agents and applying it to a combinatorial optimization problem will usually not be competitive. Yeah? So more must be done. But there is nothing that hinders you to combine reinforcement learning techniques with classical meta-heuristic approaches, to do some local search afterwards or in combination with the reinforcement learning, for example, or these mentioned tree searches. Last but not least, reinforcement learning does not always involve deep neural networks. Yeah? So in particular, when solving combinatorial optimization problem and just using the reinforcement learning as some component, then think if there are not easier ways to represent this knowledge. Frequently, you might also use some table-based approach, and these simpler approaches are then typically much easier to get running well. Deep reinforcement learning can really be tricky. That is basically said in any textbook of reinforcement learning, and I can also just agree to this fact. Yeah, so this basically concludes my talk, and I'm open to your questions, please. Emir, I think you have to switch on your microphone.
That's a good idea. That's a good idea. So thank you for this talk. And now we have reached the Q&A part, and we already immediately have a question. So we'll do 5 minutes perhaps. We're a little bit over schedule, but I think we can do a few questions. So here we have a question from Florian, where he asks, so thank you for the presentation. You presented some works using reinforcement learning to improve combinatorial optimization. Do you know some works where combinatorial optimization is used to help reinforcement learning? So we switch the story around.
Combinatorial optimization is used for reinforcement learning. Wow, interesting question. So yeah, what I can say is that there are several approaches that try to not just build some abstract model where basically the input of the observation input is mapped to a probability space of the possible actions, but where also some model of the environment is intended to be created, so model-based approaches. And there, doing some search is one fundamental technique. Yeah? So basically the idea of also doing some planning, some more advanced search within the agent. Several works can be found in this direction. Otherwise, I must really say that those reinforcement learning agents that popped up in the recent years are of simpler nature and have really clearly these neural networks in the foreground.
Okay, thank you. Okay, so we have several people thanking you for the presentation. And until we get some more questions, I'd just like to ask you briefly, so connected to the previous talk, so for example, we have simulated annealing and a timetabling problem. And let's say we want to learn the acceptance criteria in simulated annealing. So could we use something like Q-learning out of the box for these kinds of timetabling problems where there are some kind of hard constraints, which I think seems to be different from the problems where you were talking about, where it's like graph problems, so forth. It seems like the hard constraints are not that, say, maybe important as in timetabling, for instance. So can we automatically learn the acceptance function to at least help some part of the tuning?
Definitely, that has been done in several works, although quite specifically, usually targeted towards specific problems. Yeah, so I'm not aware of any approach that can immediately be taken out of the box and just plugged into simulated annealing. So as far as I have seen in the literature, there are always certain aspects that are problem specific, and so the general idea must somehow be adapted to the problem. But the principle, I think, can be tried there and might be very meaningful. Yeah. So as I said, one is to either learn the penalization, how penalization is done in the most meaningful way. And yeah, of course, you can apply there immediately ideas of Q learning to try this. Yeah? But as I said, as far as I have seen in the literature, most of the so far provided approaches are quite specific for certain problems.
Okay, so we have a question by Eugene Heather, who asks, could you elaborate how reinforcement learning without deep learning can be faster and or more robust?
Definitely, yeah. So let me also mention, I didn't mention this in my talk because I was running out of time, but actually we also did some work on a very specific combinatorial optimization problem. It's the longest common subsequence problem, a very famous problem in strings. Yeah, I don't go into details, but we tried there essentially this deep learning approach, and actually also this reinforcement learning approach following this AlphaZero, and obtained there quite nice results. But one problem really is that in this Monte Carlo tree search, you have to do quite a lot of evaluations of your neural network. And when you can replace this huge neural network by some simpler table-based approach, then this can be much faster and much more competitive, even though the actual neural network might give you a bit more precise results. But in the end, when you can perform a larger tree search, then this might be of more advantage. Yeah? So you have to find a certain balance also between the complexity of the neural network that is, or the model. Yeah, it doesn't need a neural network. As I said, we try now to go towards, to get rid from the neural network and to go towards a simpler architecture of the model that is used here within AlphaZero-like framework.
Okay, so we're going to do like one more question. There's a question by Johan Vessen, and the question is, so what kind of features are fed into the reinforcement learning algorithm? So this is particularly important if we want to scale the problem. We want to, let's say, learn on small instances, and then we hope that it works on big instances too. So what kind of features somehow that are independent of size, like we can feed to the algorithm to make it work?
Yeah, of course, the features play an important role here, but when you consider these approaches like this structure to vec, where these graph neural networks are applied, there basically the graph is the input, and the output of this graph neural network is a mapping, an abstract feature vector for each vertex. Yeah? So in some sense, in these approaches, this is what I have mentioned, the features, you do not select them by hand, but they are automatically derived from the graph by this whole learning approach. But in other problems, it's true that the selection of features is a crucial design choice, and all these approaches can be very sensitive to the selection of the features. So in the reinforcement learning framework, basically this is how you represent the state, or what kind of observation you provide as input for the agent. And there, trying different kinds of representations and providing different kinds of features really plays an essential role. Yeah? And yeah, this of course can be very problem specific. Yeah?
And is it easy for humans to understand this kind of, like how the reinforcement learning algorithm behaves for combinatorial problems?
I would say it really depends whether you use a deep neural network inside reinforcement learning or just some simple table. If you use a table, then of course it's immediately clear that the entries in the table directly indicate which variable value assignments, for example, are promising and lead frequently to good solutions. Yeah, so simpler approaches, they also have the advantage that the explainability is much more given than when you use a deep neural network where you just have this complex black box functions or the problems that these neural networks have. And again, one argument more for trying to get the job done also by simpler models within the reinforcement learning.
Okay, great. Okay, thank you for the answer. We also have from the chat, also thank you for the answer. I think we'll have to conclude the talk at this point. I'm sorry if I missed some of your questions for also the previous talk and this one, so I would suggest you send emails directly. And we would like to just take this opportunity to just thank both speakers, both Professor Andrea Schaerf and Professor Günther Raidl for these talks. I hope you clarified some things about metaheuristics for me, gave me some ideas that what I can look into and so forth. So thank you very much for these talks.
Thank you for the invitation.
So now we'll do the virtual applause.